You ever wonder how your gaming PC can crank out these absolutely mind-blowing graphics without, literally melting? Well, today, we're going to pull back the curtain on the unsung hero of high-performance computing. It's a brilliantly simple little device that tames an absolute monster of a problem.
So first, let's talk about the monster. A top-tier graphics card today can pull 450 watts of power straight from the wall. I mean, think about that. That's enough energy to run a small refrigerator. It's just a ridiculous amount of electricity getting pumped into a tiny chip smaller than a postage stamp.
And that leads to the big question, right? Where does all that energy actually go? Because physics tells us it doesn't just vanish. Every single one of those watts gets turned into pretty much one thing: raw, performance-killing heat.
Now, to fight this insane thermal challenge, you'd think engineers would use some complex pumps or crazy machinery. But nope, they use this, the heat pipe. And it is such an elegant, totally passive, and almost unbelievably effective solution to a very, very hot problem.
I mean, just look at it. It's a sealed copper tube. That's it. There are no pumps, no fans inside, no moving parts whatsoever. It looks so simple, but what's happening on the inside, well, that's where the real magic is.
Okay, so let's break it down. There are really only three key parts. You've got the sealed outer tube, which is usually copper. Then inside, lining the walls, there's this porous wick structure, kind of like a metal sponge. And then there's a tiny bit of a working fluid, often just plain old water, sealed inside in a partial vacuum. That's the whole setup.
So how do those three simple things create a cooling superpower? Well, the secret isn't really in the materials themselves. It's in a fundamental principle of physics, the magic of phase change.
And this might sound complicated, but I promise you experience it every single day. It's the exact same reason you feel cooler when you sweat. As that liquid on your skin evaporates, it has to pull heat away from your body to do it, and that cools you down. A heat pipe just does the same thing, but in a supercharged, closed loop. And this process, it's a perfect two-way street. When the liquid evaporates into a vapor, it has to absorb a huge amount of thermal energy from whatever's hot, in this case your GPU. Then, when that vapor cools down somewhere else and condenses back into a liquid, it has to release all of that energy it was holding. The heat pipe is a machine built to perfectly and endlessly master this cycle.
The sciencey term for this whole effect is latent heat of vaporization. And that word, latent, it just means hidden. It's this incredible amount of hidden energy that a fluid can soak up and carry with it when it changes state. That's what makes the heat pipe so powerful. You're not just moving warm water around, you're transporting massive packets of pure thermal energy.
All right, so let's actually follow a single packet of heat on its journey. We can see how this all comes together to create a continuous self-powering cycle.
Okay, it all starts with step 1, evaporation. The super hot GPU die instantly boils the liquid, turning it into vapor and soaking up all that latent heat. That leads to step 2. Vapor travel. See, the boiling creates a pressure difference, and that makes the hot vapor just rush down the pipe toward the cooler end. Which brings us to step 3, condensation. Up at the cooler end, the vapor hits the metal, cools down, turns back into a liquid, and dumps all its stored heat into the cooling fins. And finally, the brilliant part, step 4. The liquid returns. That spongy wick structure uses capillary action, the same thing that lets a paper towel soak up a spill, to passively pull the liquid right back to the hot end, ready to start the whole cycle over again. It's a constant, silent, and incredibly efficient little heat engine.
So yeah, this is some fascinating physics. But why does it actually matter for you and your computer? Well, this is a perfect example of the direct link between cooling technology and raw computing power. Just take a look at these numbers. The thermal conductivity of a solid bar of copper, one of the best heat conductors we have, is around 400. The effective thermal conductivity of a heat pipe, it can be over 100,000. No, that is not a typo. It is hundreds of times more effective at moving heat than a solid chunk of metal. It's like comparing a garden hose to a fire hydrant. It's not even in the same league. And here's the bottom line. That incredible cooling efficiency is the reason chip designers can push processors to insane speeds and cram billions of transistors into tiny little spaces. I mean it. Without the heat pipe, the powerful GPUs we rely on for gaming, for AI, for creative work, they just couldn't exist. They would literally cook themselves in seconds. So let's just sum it all up. The humble heat pipe is a completely passive system, zero moving parts. It uses the basic physics of phase change to move heat at incredible speeds. It's orders of magnitude more effective than solid metal, which makes it an absolutely essential, cornerstone technology for pretty much all modern high-performance computing. It really is a genius piece of engineering that solved a critical problem. But as our processors keep shrinking and getting even hotter, it really makes you wonder, right? What comes next? What's going to be the next passive, elegant solution that can tame the even bigger monsters of tomorrow?